go. And chapter 2 finished on Friday. Now we look at resistors and capacitors. Sorry, capacitors and inductors. We're done with resistors, or at least resistive analysis. So up 03. Chapter 3. Okay. Inductors and capacitors. In terms of energy, what is different about inductors and capacitors from resistors? They store energy, absolutely. That's actually where the name for the capacitor comes from, because it has a capacity for storage. Okay, so inductors and capacitors are energy storage devices. Unlike resistors, which receive energy but dissipate or release it in the form of heat. Okay, anytime energy transfer take place, there's always some energy lost due to heat. That's just the nature of things. That's physics. So these are energy storage devices, unlike resistors. They are still passive, meaning they do not have any energy supplying capabilities of their own. Okay, they can receive energy and they can only supply that same energy back into the circuit. Okay, they do not have any energy of their own. So they can receive and supply energy. That same energy. Okay, receive and supply that same energy. Inductors store that energy in a magnetic field, and capacitors store the energy in an electric field or electrostatic field. So inductors store it in a magnetic field, and capacitors in an electric field. Capacitors and inductors are kind of duals of each other, very similar, but also opposite in some instances. And that is going to be true throughout the rest of this course. Okay. So again, capacitors and inductors are energy storage devices. They do not have any energy generating capability of their own, but they can receive energy and then they can discharge it back into the circuit, depending on the circuit conditions, of course. So they can receive energy and discharge it back into the circuit at a later point in time. So in chapter 3, we will talk about the theory of inductor and capacitor. And then we will look at the equations that govern the relationship between the voltage and current for the inductor and the capacitor. Okay. We won't delve too much into the physics. Again, this is not a physics class. This is a electrical engineering class. So we'll look at basic construction. We'll look at a little bit of the concept of the physical capacitor and physical inductor, but we will not delve too much into the device physics of things. We'll stick to the engineering side, meaning we'll look at the equations for voltage and current for both. Now, energy can never be transferred in an instant, right? You cannot like flick your fingers and transfer energy in an instant. So energy transfer takes certain amount of time. Whether the devices are receiving the energy or whether they're delivering it back into the circuit, there's always a finite amount of time that is required. If you think of this as a bucket of water that you're filling, the time required depends on the size of the bucket as well as the pipe dimensions and the flow of water. And I like to use the analogy over and over again because it makes the most sense. If the bucket is small, it takes less time to fill it up. If the bucket is large, it takes longer. If the flow of water is fast or the flow rate is high, then again, that also affects how fast it's going to fill up. If the flow rate is slow, again, time is low. Time is less. In chapter 3, we'll just look at the basic equations for voltage and current. In chapter 4, we'll look at the equations that are required to solve for the voltage and current during the charging and discharging process. So right now we introduce the capacitor and inductor and we talk about the voltage and current. In chapter 4, we look at the energy transfer we look at the voltage and current during the energy transfer process, meaning when the energy is being received by the devices and the energy is being discharged or being supplied by the devices. Okay, so they are kind of chapter 4 flows from the end of chapter 3, right? So let's begin. We'll start with the inductor first, and we'll talk about magnetism. Okay, again, as I said, inductors store the energy in a magnetic field. So a couple of slides on magnetism and then electromagnetism. Okay, magnetism plays an integral role in every device that we use today, whether it's a generator, motor, television, radio, cell phones, wireless charging, anything to do with wireless has electromagnetism. Okay, so I'll put TV, radio, our cell phones, wireless communications. Cell phones are wireless communication, cordless phones, satellite communications, mobile communications. They all use the concept of electromagnetism. Okay, now over the last few centuries, a lot of people have done a lot of research over electromagnetism. And in general, any scientific topic, any topic for that matter, can be worked on at the same time by multiple people who are unrelated to each other all around the world. It's the person who publishes first or makes their work known the first that becomes famous, and their name gets associated with it. Okay, so in the early 1800s, French physicist named André Marie Ampère was the one who came up with Ampere's circuital law. And so, again, Ampere is what we use for, the units for current. And then the years succeeding after that publication, we had scientists and researchers, Carl Gauss, Maxwell, who else? Who am I forgetting? Faraday, Michael Faraday. All of those people did a lot of research. Maxwell came up with a set of equations for electromagnetics that is actually considered to be the foundation of the entire field of electrical engineering. Maxwell's equations, they're very famous. If you have an EE friend, you can ask them about it and how hard it made their life. Anyway, so that's where the electromagnetism principles come from. Now, every conductor, when a conductor meaning a material that is capable of transferring charge, has inherent resistance, capacitance, and inductance. Okay, even if you take our 100-foot extension cable, the orange ones, bright orange ones, you plug it into a wall, which has 120 volts coming out at the power outlet, 100 feet away, you would still expect 120 volts. But the cable inherently has resistance, inductance, and capacitance. But the resistance does not rise to the level of interference. Meaning if it's 120 volts at the outlet, 100 feet away, we'd still expect 120 volts. In real life, that cable does have some resistance, but again, it does not rise to the level of interference. That 120 volts is not going to drop to like 100 volts. It might drop by like 1 volt perhaps, but not enough to interfere with the normal operation of things. If you take an HDMI cable and you plug it into, let's say, a computer output or a gaming output, and you connect it to a TV display 100 feet away, then the resistance, the inductance, and the capacitance of that HDMI cable will rise to the level of interference. Okay, that's why longer cables are more expensive. They have to be engineered or designed in a way using specific material such that the resistance is very low, the inductance would be very low, and the capacitance would be very low. Now, that brand comes to mind, that Monster cables, which would charge like $50 for like a 6-foot cable, that's pointless. If it's within like 6 feet or so, but $1 cable is the same as like $10 as the same as $100. it won't rise to the level of interference. Okay, so the values of those components will not interfere with the normal operation of things. So coming back to the point is, a magnetic field is present around every wire that is capable of carrying current. When current flows through a conductor, a magnetic field is established due to the magnetic flux that is established around that wire or around that coil. And it's the magnetic flux lines are typically given by the right-hand rule, meaning if you grab that conductor and you point your thumb out, then if the current you point your thumb in the direction of the current, then the fingers point towards the direction of the magnetic flux lines. Magnetic flux, by the way, again, going a little bit into the physics, is the same as made up of photons, but they are not within the visible spectrum, meaning the frequency of those photons, frequency of that magnetic flux, is not in the physical spectrum, visible light spectrum. Okay, but they are the same quantity, they are the same thing. Anyway, so this is given by the right-hand rule. Where your thumb points in the direction of the current and your fingers point in the direction of the magnetic flux. This is very weak. As I said, it does not rise to the level of interference. Okay, it's very weak. However, if you form a loop around it, now you have magnetic flux lines, right? They would all align. They would all align together. And if you can visualize, there's a loop running in that coil, sorry, in that conductor. They would all point towards the inward or outward, depending on a perspective, and they would all point towards the same direction. Okay, all of them would point towards the same direction. If you take that single loop and you form multiple loops around it, you can see that the magnetic flux lines go around every single coil, plus a longer or larger line is established that goes through the core of that coil, flowing, well, in this illustration, flowing from the right or entering to the right and exiting from the left. And it imitates a permanent magnet. So if you take a current carrying conductor and you form several loops, it imitates the magnetic field of a permanent magnet. With a north and a south pole. But again, this is very, very weak. Field is weak. And that's just the physics of it, because the loop has empty air through its core. And then researchers, well, somebody had the idea of actually taking a ferrous material and inserting it in the middle of a coil. And what that does is it allows the magnetic flux lines to be easily established around that loop and around that core. And so thus, the insertion of a ferrous material like iron, steel, which is again nothing but iron, cobalt, etc., it strengthens the magnetic field. Strengthens the magnetic field. And that is the working principle of an electromagnet. You have a current carrying conductor wound around a ferrous material or ferromagnetic material, and it establishes, it establishes a very strong magnetic field. Okay, very strong magnetic field. that can certainly imitate or use in place of a permanent magnet. All right, any questions so far? Again, we won't get into the device physics much beyond this. So, current flows through a coil of wire, spiral coil, establishes a magnetic field. We call that component as an inductor. The symbol is simply a spiral loop, typical to a resistor. We can draw it horizontally or vertically, depending on our requirements. I, in electrical engineering, is reserved for current. C is reserved for capacitor, which seems counterintuitive to me because current is used a lot more than you'd encounter current a lot more in electrical engineering than you would encounter capacitor. Anyway, so the inductor is noted by L. Uppercase L. Lowercase l is for length. Uppercase L is for inductor. The unit is Henry. Henries. Anyone know who it's named after? Anyone? Just trivia. It's an American physicist named Joseph Henry. Magnetic flux. Anyone know it's named after? Weber. And then magnetic flux density, Tesla. He did a lot of work. So if you recall the first day of class, I talked about the war of current and I mentioned Tesla versus Edison. And I also mentioned Tesla did a lot of work in electric motors, transformers, coils, inductances, wireless charging. Anyway, inductor and capacitor are both passive components. So they follow the passive sign convention or the passive reference configuration. Again, passive sign convention or passive reference configuration. Meaning the current for an inductor and a capacitor flows from high to low, from plus to minus. So if you're given a voltage polarity across an inductor, current always goes from plus to minus, similar to a resistor. And if you're given a current direction, then the point of entry is plus and the point of exit is minus. Passive sign convention or passive reference configuration. Again, it's a passive component. It's not active. It cannot supply any energy of its own. Okay, they can only store and release energy in a magnetic field. Before I go there, 1 Henry is noted as the inductance that can store 1 volt across its terminals for every change of current through it in the amount of 1 ampere per second. Okay, it's quite a mouthful, but think of it this way. If current, and we'll look at equations again in a few slides, if current through a current flowing through an inductor causes a voltage to appear across it, if the current is constant, meaning does not change its value, then the voltage across that inductor is 0. In order for a voltage to appear across an inductor, the current has to change. So if current changes, then a voltage appears across the inductor. And this happens during the energy receiving and the energy delivering stage when the current is actually changing, right? If an inductor is at 0 amps and you apply 1 amp of current, then the current does not instantly reach 1 amp. it takes time for it to reach 1 amp. So during that time, when it goes from 0 to 1 amp in that inductor, you will see a voltage across that inductor. When the current reaches 1 amp, that current is now constant, the voltage across the inductor goes to 0, right? So 1 Henry of inductance is the level that can store or can show 1 volt across its terminals for every change of current at the rate of 1 ampere per second. Physical construction of an inductor is simply a coil. You take a current carrying conductor and you wind it up in a coil, and that's an inductance. There's also very well known for installers. If someone comes to install electronic components in your residence, and instead of leaving the extra cables in a loop, they would actually form like a kind of like a rectangle with that, but they will not leave it in a loop. Okay, when you leave it in a loop, it's going to cause the magnetic field to increase its strength, not by much, but just a little bit. And sometimes that could interfere with the normal operation of your electronic devices. Let's see. Okay, so physical construction of an inductor. Actually, we are almost out of time, and you know what? I'm just going to stop here. We'll pick up here on this slide, and I'll just take questions if anyone has any questions. Yes. Once it reaches a constant level of current, yes. Is there any other question in the back? So, okay, we'll stop here today. I'll end class here today, and I'll see you all on Wednesday. I'll keep the Zoom meeting open if anyone has questions, and of course, I'm here in the classroom for the next hour and 10 minutes. What happened to